Introduction to Granular Mechanics. And so it's really a course which is related to understanding how particulates or particles, how they flow, and what are the ways of describing the behavior of particulate materials. So, what is granular material? So it's basically, you can say, a collection of particles. Okay, so there are many, you can think of many examples. Sand, gravel. But if you're looking in industry, then maybe catalyst pellets. They may be usually cylindrical or whatever, but then in agriculture and food technology, you are talking about grains, which are there. In the pharmaceutical industry, there may be tablets or pills. And also you can think of seeds in horticulture. In the mineral industry, you can think of mineral ores. Then you can think of processed foods. Examples could be even things like potato chips or kurkure or something like this, which material needs to be handled. And there's a huge number of other things like people even talk about asteroids as being granular materials, or if you look in the Arctic and Antarctic, there's like large fields of ice pieces which are called ice floes. So they are floating on the surface of the sea, and then they are like a granular material, and so forth. So you can have many examples. Now, in the first part of the course, we are going to look at cases where because even though you say, okay, here you have sand, but it's actually sand plus air. But the viscosity of air is low enough that you can actually ignore the presence of the air, and so forth. So in most parts, fluid could be neglected in most parts, in many of the problems. And this is particularly the case when your particles are somewhat larger in size. Let's say, when your particle size is more than about 100 microns, then your fluid, interstitial fluid, can be neglected. Also, surface charges can be neglected in these cases. So, particles won't be sticking to each other and so forth, because they're big enough that the mass of the particles is going to be much larger than the surface charge. So, if you have large enough particles, then you're actually just looking at you can imagine just particles that are interacting with each other in a vacuum. However, in some cases, and perhaps towards the end of the course, we look at this. In some cases, fluid may be important. And this is important usually when you have small particles or high velocities. And these high velocities could be either high velocities of the particles. If they're moving very fast, then drag forces become important. Or you've got, let's say, very high, fluid velocities, and so they also entrain the particles and so forth. So in most of what we are going to study, we'll neglect the fluid, but perhaps in some small way we may study the effects of fluid towards the end of the course. Okay, so for most part of the course, we just imagine that these particles are moving around in a vacuum. So if you look at where do granular materials come, I've already given you examples, so you can guess. But there are many places where granular materials are processed in industry. And the basic point is that more than 50% of products of the chemical industry are granular materials. And there's that most of the stuff that is made. So in the petroleum industry, of course, you have petrol, diesel, and so forth. But many of the other industries, whether you look at detergents, many of them are in solid form. Whether you look at bulk chemicals like soda ash or whatever, in huge quantities they're made. They're all particulate materials. And so very large, you look at things like cement, fertilizer, all are solids. And also, of course, raw materials, many of the starting materials, the catalysts, things like adsorbents, they're all solids. So if you actually see the granular materials are actually processed in huge quantities. Even if you look at the pharma industry, the pharmaceutical industry, and there is a course that's running in our department on chemical engineering applications to the pharma industry. Even there, there's a lot of important things. Like one of the important applications is mixing of powders. Usually the active ingredient is in a very small quantity, and then you have to mix it in some large amount of inert material. But here the mixing has to be perfect, because you can't have one tablet which has more of the active material and another tablet which has less, because obviously it could have a big effect on the effectiveness of your medicine. So, but of course there's a lot of handling of materials that is important, storage and all. They are also carry out a number of coating processes, because if you see your tablets, usually some of them will have some nice bright colored coating on it just to protect the material inside, and so they'll have special coating. So again, that is another operation that they carry out. Drying, coating, all these things have become very important. And really the key thing is that the processing and handling of granular materials is very important in many industries. And so this is the motivation why we would like to study it, and particularly in chemical industries it's quite important. But in addition to industry, there's many granular processes in nature also which are of interest. And in natural systems, you can think of things like sand dunes, where there are these huge piles of sand which move when the winds blow. Then these days in the paper you read a lot about this, but it's become very important. Landslides, avalanches, these are all examples of granular material. In some cases fluids are also very important. Then what about the path that is taken by rivers? Because usually what happens is that as the river flows, it carves out a channel, but that channel never remains straight, it always meanders. So that is again a granular flow problem. Then you would have seen the rings of Saturn. Those are also a collection of granular materials and so forth. So there are many, many examples in nature. And this is also another motivation why people study how granular materials will flow. And of course, once you are talking about processing, you can think of many unit operations. Many unit operations involving granular materials. These are like, you say unit operations, what it means is that these are the typical things which are done in the industry. So if you have no fluid effects, that we'll call that as dry granular materials. So it's just particle to particle interactions. And there are many examples. For example, storage in bins. And we'll analyze this. What is there to study in storage in bins? So that is one thing that's quite important. Then you can think of heaping and pouring. Then crushing and grinding. This is a very common operation that you start with larger sizes and then you have to reduce the size. So I also mentioned this mixing. These are very common operations with particulate material. Then you may have conveying, which can happen through screws, belt conveyors, and so forth. Chutes, which are basically just channels which are inclined and the material flows under gravity. And you can also have things like sieving, other separation methods. So these are all processes which are used in industry on a very common basis, in addition to other things like coating, agglomeration, and so forth. Granulation is what is done to make, you put in some liquid or something which will make particles come together and agglomerate into larger particles. So these are just some of the examples that are there. And then when you have fluid plus granular material, so where fluid forces are also important, there are many examples. Fluidization is one of them, and hope that towards the end of the course I'll discuss this. Pneumatic conveying. So this is again a way of transporting particles. It's like pipe flow, but you just blast air which carries the particles along. You have things like filtration, then sedimentation, and then of course we have packed beds and the flow through packed beds and stuff like that. So all of these things are quite important, and they show up in a number of industrial processes. And if you sort of look at the curriculum in many of the engineering disciplines, we learn very little about how to do many of these processes. So what you find is that, in fact, performance of many granular processes is below par. And I'll try and explain why. And so, basic problem is that designs are not optimal. So we know that most of the fluid systems we have very nice designs and we have a very good understanding. But in granular systems, this is not so. So one of the reasons why this happens is because the development of the fundamentals of granular mechanics has lagged compared to fluid mechanics. Okay. So, I've just got some dates here. So, for example, hydrostatics was starting to be understood from the time of the Greeks. That is many BC. Then the idea of viscosity and inviscid flow. So viscosity, from the time of Newton, that is around 1500 AD. And, the Navier-Stokes equation, which is the fundamental equation for fluid flow, was already developed by 1800. And then you had Reynolds by 1883. He had already discovered turbulence. So you all would have all come across fluid turbulence. And then, things really advanced, and you had the boundary layer theory by Prandtl in 1905. And, by 70s, computational fluid dynamics has already come by 1970s. So you could actually start solving quite complex problems using computers by the 70s. And so today, it's really for single phase fluid flow, there's no problems. And even for multi-phase flows, you can get quite good. So there is a good understanding and there are good techniques. And one of the reasons is that, you can have, it was easy to study because you could always look inside fluids. So if there's water flowing, you can just put in a few tracer particles and you can see what's going on. You can look inside and you can make measurements today with, very sophisticated techniques called PIV, particle image velocimetry. Gives you very detailed flow field information. So, the field advanced because the experiments were easy to do. You could see what was going on and so forth. On the other hand, if you look at granular materials, well, it's a lot more difficult. And really, you had friction laws by Coulomb. So this really helped in the development, but this was as late as 1750. And then Hagen did some work on the hourglass and so forth around 1800. So this is the same Hagen as Hagen-Poiseuille for the pipe flow. Reynolds also did some work on uh, dilation of packed beds around 1880 when he was looking at fluids also. And then much later, Roscoe and all looked at soil mechanics, but this was already 1930s. So they were more interested in building foundations for buildings and stuff like that. So how do you model what happens to soil when you add stresses on it? And then Bagnold, he looked at flow, actually rapid flow, and that was in 1954. And he was looking at the flow of sand, and he came up with the first theories. And then Savage and Jenkins, they looked at more rigorous models similar to Bagnold, which is based on kinetic theory around 1970s. And most recently, Pulikin and Job. They looked at some dense flows, and this was around 2000. So you can see that this has been delayed by quite a lot, but even today there is no equation equivalent to Navier-Stokes equation. And so really it's still difficult to model the flow and so forth of granular materials in general. But over the last 2 decades, since 80s, there's considerable progress in the development of the field. And what are the tools? Well, now we can look inside. If you have a bed of sand, you can't make out what is going on inside simply because you can't see inside. Even if you take a bed of glass beads, you can see what is outside, but even if the glass beads are transparent, you can't see what's going on inside. But now people have been using things like X-rays, MRI, and so forth, which give a insight into what's going on inside the flowing granular material. And then, of course, you have computational methods which can give very detailed information. And this comes under what is now called DEM, discrete element methods. And we look at this. So as a result of this, there's been a lot of advancement that has happened because of experimental and computational developments. And so, in this course, we do have substantial, real sort of techniques and knowledge to impart. It's not like nothing is known. Now, a lot is known, and we'd like to sort of put it together and tell you about it. So, what is the course outline? This is on Moodle. So the course objective is to give an introduction to the fundamentals of statics and flow of granular materials based on the current understanding of the subject. So we'd like to use the most recent developments and tell you about them. And then experimental and computational tools for the analysis of granular flow will be discussed. And then how can we apply all this to practical problems? So we'll look at some of those things. So this is a sort of tentative schedule. I've already told you about granular materials and what is the typical operations. And then I'll spend a bit of time on some basics, like how do you characterize granular materials, what are particle-particle interactions, like what forces are there, like what is the frictional force, how the collisions occur, deformation of particles, cohesion between particles, and so forth. And then so these are at the particle level, and then at a more gross level, things like angles of repose, and some qualitative aspects of the characteristics of flowing and static materials, and some flow regimes. So this is just sort of some basics of these, because granular materials are in fact quite different from fluids. So I'd like to tell you about that. And then I want to spend some time on discussing some tools. So I'll spend a short time looking at vectors and tensors, and how, because I'm going to use them, so I want everyone to have the same nomenclature. Has everyone done vectors and tensors in some course or the other?
Yes, sir.
So everyone is quite familiar. So this will be like some kind of a review. I'm not going to spend too much time on it, but just as a review. How about the undergrads would have done? How about Nikita? You have done this, vectors and tensors?
Yeah.
You're familiar?
Yeah.
Oh, good. So this will be some sort of repetition, but I'll just go over it just so that, because everyone has different ways of writing these things. So I'll not spend too much time, but I'll go over it. Then I want to just immediately get into the numerical methods, because I want you to do, I want you to get on hands-on onto these. And so I'm going to discuss, these numerical methods they actually follow every particle. So you know the x, y, z position of every particle, you know the velocity of every particle, and then you have to follow it. And the particle moves according to Newton's laws. That is, acceleration is just equal to the sum of forces divided by the mass of the particle. So we will look at those. So I'll tell you about what is the inside of it, but then I'll introduce you to a open source software called LAMPS. And this one is a yeah. So this software is, it's free to download. You can download it onto your computer, laptop, or whatever. And it's very easy to then do simulations of granular flows and so forth. So I want you to all learn how to use this, but I want to do this early in the course. And then, we will solve some simple problems using these things. Okay, so this is the tools part. Then I'll talk about very slow flows or statics. And then there, the key thing is this Moore-Coulomb theory, and then a little bit about critical state theory, which is an extension of this. And these things are important in, what is the statics of bins and hoppers and so forth. So we'll look at some examples like that of very slow flows. And then we'll look at rapid flows, starting with Bagnall theory, that is the first one I told you, and then granular kinetic theory and how we can apply them to some simple problems. And then, as I said, that more recently we have come across this theory for dense flows. Is an empirical model called the mu-I model. Again, we'll discuss this and see how it can be applied. And then we look at, you know, some things called surface flows. So in these types of flows, you can actually make some approximations that the flowing layer is quite thin, so you can just average across the layer and then you get simple equations which you can apply to many systems. And then we'll talk about mixing. And if time permits, after all this is over, then I'll talk a little bit. I've not written it down, but we'll do a little bit about fluidization and so forth. So here are the meeting times: 8:30, 9:30, 10:30. And then this is what this is again tentative, and I'll take feedback from all of you. So I'd like to reduce the weightage of mid-semester and end semester test. Um, we'll have some homework assignments. I don't know, maybe more than 3. And there will be a project. The project will be based on lamps. That is the software we learn. So there will be some problem you have to solve using lamps. And I'll have a number of in-class quizzes. That is just during the class, maybe 10-15 minutes. Towards the end of the class, I'll have some simple quiz, but I'll have a large number of them. I've written 8, but I don't know how many, depending on. So once some topic is complete, I'll just have a quiz. So that way everyone is up to date on that. So right now it is like this. So far, I would say the best book for the course would be this, An Introduction to Granular Flow by Kesava Rao and Prabhunath. But there are other books also which have been written, and I'll probably listen, I will look at those, but not in so much detail. Okay, I didn't give my name, but my name is Devang Kakkar, and the teaching assistant for the course is Niladri Ray. Okay, that's him. Okay, so any questions? Okay, so just to get to know you, can you just briefly, can each one of you just briefly introduce yourselves? Uh, just say your name and what are you doing, what is your academic program, and so forth. So I'll just call out the names, you just, so I can see who you are. So Nikita.
Hello. Hello, myself Nikita. I am a chemical engineering second year MTech student, and I am from Kerala.
Very nice.
I am now.
Yeah, go ahead.
That's no, sir. I am doing project under Devankakkar sir only.
Good. Uh, Rahul Yadav.
Hello, everyone. This is Ravneto from Kanpur, and I did my PhD in
Rahul, we couldn't hear it. Maybe you can just put it in the chat box. Okay, yeah, the there's a question. Will the project be individual or in a group? This will be group projects, so maybe 2 or 3 people together. If you want to do it individually, you're free to do it, but maybe up to 3 students together can form a group and do it. Okay, Jay or Jay Kumar.
Hello,
Yeah, go ahead,
I am
Jay.
Jay, uh, fourth year chemical engineering undergraduate, uh, BTech,
Very good.
and I am from
Malika Arjun Reddy.
Yes, sir. My name is Mallikarjun and I'm a dual degree student in chemical engineering department.
Good. And Nanak.
Hello.
Oh.
Hello, myself Nanak. I am chemical engineering student, BTech 4-year program.
Fourth year.
Yes, sir.
Okay. Yash.
Hello. Hi, sir. I'm Yash. I'm also a BTech 4th year student in the chemical department, and I'm from Gujarat.
Good. Good. Kiran.
Hello, sir. I am second year. I'm tech student in chemical engineering. I am from Kerala. I'm doing project under Sardi, sir.
Very good. Azim.
Hi sir, good morning
Hi.
everyone. Myself Azim Memon. I am PhD second year in chemical engineering and I work under Professor Divankar.
Thank you. Jangid.
Hello everyone, my name is Roshan Jangir. I am fourth year BTech. I'm student in fourth year BTech Chemical Engineering, and I'm from Maharashtra.
Very nice. Devidas.
Good morning, sir. Good morning, everyone. I'm Devadas from Department of Energy Science and Engineering, and I'm currently doing my MSc PhD dual degree under Professor Manaswita Bose.
Very good. Sahu. Sahu, are you there? We can't hear anyway. Maybe can you put an introduction in the chat?
Hello,
Yeah, go ahead.
I'm Khokon Sao. I'm a PhD first year PhD student in the Department of Aerospace Engineering under the supervision of Professor Sudarshan Kumar. I am from West Bengal.
Very good, very good. And Sajal Pole.
Hello. Hello,
Yeah.
sir.
Yeah.
Sir, myself Sajal Podle. I'm from West Bengal. I'm currently doing under project under the Professor Rakul Dasgupta, and I'm second year PhD student in chemical engineering department.
Second year PhD student in chemical engineering.
No. I'm doing MTech, sir. MTech second year. Yeah.
In which department?
Department of Chemical Engineering.
And who's your guide?
Rakul Dasgupta, Professor.
Rakul. Okay. Very nice.
Thank you, sir.
Vishwas Rao Soham. Hemant Soham.
Good morning, sir. I'm Soham Vishwasrao, fourth year chemical engineering. I'm from Maharashtra.
Your name is Soham.
Soham.
And can you just say again, you're from where? Which department?
Chemical engineering, fourth year.
Fourth year chemical engineering. Okay, BTech.
BTech.
Very nice. And Yashmeet?
Hello, good morning, sir. My name is Yashmeet. I'm also a fourth year chemical engineering student. I'm from Ghaziabad, UP.
Hey, great. Okay, so very nice to meet all of you. Do you all have any other questions that?
So there was one more participant here.
Who's that?
Priyanshu Ranjan Gupta.
Go ahead, Priyanshu. I missed you.
Good morning, sir. I'm Priyanshu Gupta. I'm a MTech second year student. I'm working with Professor Sanjay Mahajani.
Okay, very nice. Very nice. Okay, great. Okay, so welcome to everyone. And I can now we have a few minutes, so I can now continue on the. So the question is, will the quizzes be surprise or will they be informed? No, there will be no surprise quiz. I will let you know at least a few days in advance. Okay, and all the quizzes will be on Moodle. So they will either be multiple choice or some simple calculation where you have to put in the number. Okay. So let me just say what we are going to do next, which is actually supposed to be for the next class, but let me just start that. So this was just some basic introduction. And then, what I'd like to get to is the next topic, which is on characterization of particles. So the most important one is really to look at particle size. And there are a large number of methods because of that. But first, let me just start with geometric characterization or shape characterization. Here, there are not so many quantitative techniques. But there are more qualitative. So as you know, we've seen so many different examples. So how do we characterize the shape of particles? And so, people put them into categories, and so you can say that, okay, the particle is acicular or needle shaped, something like this. And an example of this could be rice husk. Then you could have something that is angular, and here it could look like this, and the example could be gravel. Then you have crystalline, and the example is salt, or maybe even sugar, and many other such things. And then fibrous, example could be jute, flaky or plate like, An example of this could be mica. Dendritic, where you have sort of complex fractal type shape. Example of this is snowflake. And then of course you have something that's called granular or rounded. This example is a sand particle. And then of course you have the regular geometric shapes like say spherical or cylindrical or whatever. But there are many, many of the manufactured products like polymer pellets and so forth, they may be just around like this or so forth. So, this just helps to, once you have things classified, then, if you're trying to choose some equipment or so forth, you can do the choice based on, manufacturer will tell you that my product is good for, angular particles, or it's good for fibrous particles or whatever. So then, you can choose that particular. This is quite qualitative. Now, if you have particles which are sort of roughly spherical, then there is a quantitative method and that when it's close to being a sphere, you can define a quantity called sphericity, which is often denoted as phi s. So has anyone come across this term before? Sphericity? Nobody? We'll go into it in more detail next time, but I'll just say that it's just a measure, a ratio of surface areas. So surface area of equivalent sphere, that is a sphere of the same volume as the particle, divided by surface area of the particle. Now, why is this a measure of sphericity? Well, you know that the sphere has the smallest surface area per unit volume. So if you take two particles of the same volume, then the surface area of a non-spherical particle will always be more than that of a sphere. And if you take the ratio of their surface area, then you will always get a number that is less than or equal to 1. So if the sphericity is close to 1, then the particle is close to being a sphere. If it is far from 1, then it means that it is deviating from a spherical shape. So this is one way of characterizing, and we'll do some calculations of this in the next class. So the next lecture is tomorrow at 9:30, and I hope to see you there tomorrow. Okay. So let us end today and look forward to the rest of the course.